Hello everyone, this is Coach Tapman, and today we are going to be talking about levers. So, what is a lever? Well, it's a simple machine. A lever is a simple machine consisting of a beam or rigid rod pivoted at a fixed hinge or fulcrum. A lever is a rigid body capable of rotating on a point on itself. A lever amplifies an input force to provide a greater output force, which is said to provide leverage. The ratio of the output force to the input force is the mechanical advantage of the lever. And this is from Wikipedia. You guys know, as much as I love Wikipedia, sometimes they are incorrect. A lever is not always something that amplifies an input force, and we will see that in just a moment. So let's visualize. Really, there are three types of levers, and we can see the examples for those here. We can see what it looks like when somebody just uses a rod or a rigid beam to pry something. So you can think of the claw side of a hammer or a pry bar, whatever it would be, works as a lever. By having two opposite ends, this also works like a teeter-totter. You can see a wheelbarrow where you have this load that is sitting somewhere in the middle of your rigid beam and your fulcrum on your wheel, and the effort is being applied further along the beam to lift that the wheelbarrow. And then finally, for the Class 3 lever, this is what I was talking about. There's not always an amplified or an amplification on the input force. And so what you actually have here is you have some kind of a beam, or the resistance is actually farther from the fulcrum than the effort is, which would in turn mean that the effort needs to be even greater than just lifting whatever the load is that you're trying to lift to create movement and motion in the direction you want it to be. And so, again, there are three different types of levers. And levers are certainly important for the 2020 and 2021 seasons for Science Olympiad because you need to use them in your design. So what is the mechanical advantage for a lever? Well, it's very straightforward. On levers, there is always a resistance load and an effort load. Resistance force and an effort force. Resistance is often associated with a load. So think of the load or the resistance as whatever it is that you're trying to move with your lever. Whereas the effort is wherever you would be applying an effort or a force to move the resistance or load, weight or force or whatever it would be. And so the distance actually from the fulcrum to the effort and the resistance is how we calculate our ideal mechanical advantage. So we see here from the equation that the ideal mechanical advantage for any lever is the length or the distance or the length from the effort to the fulcrum over the distance or the length from the resistance to the fulcrum. And that's how we calculate ideal mechanical advantage. So now we're going to go ahead and do an example for the mechanical advantage of a lever. So, what is the mechanical advantage of a lever with a distance of 5 meters from the effort load to the fulcrum and a distance of 2 meters from the resistance load to the fulcrum? Well, right off the get-go, we can write down our equation for the ideal mechanical advantage of a lever. So the ideal mechanical advantage is equal to the length or the radius or the distance from the effort load over the length or radius or distance to the resistance load. Well, we know from our problem 5 meters from the effort load to the fulcrum and 2 meters from the resistance load to the fulcrum. So we know that our L sub E is equal to 5 meters. We also know that our L sub R is equal to 2 meters. So then, to calculate our ideal mechanical advantage, we will have 5 meters over 2 meters. These will cancel out, leaving us with a mechanical advantage of 2.5. Okay, well, that's great. Well, what else can we learn looking at our question? Draw the two possible levers below. Okay, there's 3 different types of levers that we've discussed already. A type 1, a type 2, and a type 3. If we remember the diagram that we looked at on our presentation, we remember that a class 1 lever looks something like a teeter-totter, where you have some resistance and some effort. Okay. We also know that there's no real restraints on how far the effort has to be. We'll go ahead and draw that here. There's no real restraints on how far the effort has to be from the fulcrum, and there's no real restraints on how far the resistance has to be. And this is our type 1. So type 1 looks like it's all right, because we have a length of 5 for our effort and 2 for our resistance. This checks out because there's no real restraint. Let's look at our type 2 lever. For our type 2 lever, we know it looks something like this, where we have some resistance close to the fulcrum and an effort that is necessarily defined as farther from the fulcrum. We'll call this R1. We'll call this R2. We know that for type 2, R1 necessarily has to be larger than R2, or at least equal to, but I guess that's not really a lever. So in our scenario, is our R1, the distance from the effort to the fulcrum, larger than R2, the distance from resistance to the fulcrum? And indeed it is. So again, type 2 lever is successful. Judging by the problem statement, you can see that the type 3 lever is probably not possible, but let's go ahead and look at why. In a type 3 lever, we know we have some kind of fulcrum here, along with your effort, some kind of resistance. Now, if we use the same terminology that we use for our type 2, we have R1 is the effort to the fulcrum, the R2 is the resistance to the fulcrum, meaning that R2 is necessarily greater than R1. Now again, looking and seeing that our R2, or our resistance load, is 2, and our R1, or our effort load, is 5, we can see that 2 is not greater than 5. And judging from this, we come to the conclusion that this is indeed not possible to be a type 3 lever. Therefore, the two possible levers would be our type 1 and our type 2 lever.